Hi everyone, my name is Quinn. I'm from Pukyong National University. Come to this conference. Today we will talk about a problem microplastic pollution in the ocean. With a topic the behavior of microplastic in a near submerged structure on the beach slope. Based on CFD's model, I will start with introduction. We know that now the pollution microplastic in the ocean is a global problem. Almost culture develop and developing. Special scientific interests show until 2022 year about 4,300 studies have already published related pollution microplastic. In the figure 1, so a spatial distribution of major microplastic concentration. And this figure shows two locations, Asian and Arctic. We can see that the location have microplastic concentration higher than another area. And besides, in ocean, the Pacific Ocean have concentration microplastics higher than uh, Indian Ocean, and Indian Ocean have a microplastic concentration higher than Pacific Ocean. Oh, sorry, this is Atlantic Ocean, and and why has some studies say that the location is meaning Asian and Arctic. The culture developing, so they're using a lot of particle. It will be due to pollution particle at the location. And so we can say that microplastic present everywhere in our planet. Occurrence and abundance of microplastic in the environment, and abundant in water system, and abundant in sediment, and abundant in marine organisms, and microplastic abundant in the ocean and near shore. So go this study and you investigate behavior of microplastic near shore on the beach slope. Material and methods. The first material and number one tank water model. In figure 2 shows the schematic of CFT waste flow. This figure shows the dimension of 10 meter long and 0.6 meter high. This figure shows A is the waymaker and B is the structure. The structure have already in tone at 8 location equal 4.2 meter with 2K WS1 have a height equal 0.2 meter and WS2 height equal 0.28 meter. Besides, we have some parameter such as way height and still water and whaling and fish surface. And cycle yellow, we have these locations really particle to simulation particle behavior in the near shore on the beach slope. Number two, the geometry model. Figure 3 shows the grid meshing for beach slope in figure 2A, and WS2 in figure B, and WS1 for figure B, and WS2 for figure C. And the two-dimension numerical grid size 0.05 meter and beach slope equal 5 degree have already designed, and beside Thai with rectangular head is using addition two phase air and water uh, have this phase by we can see that is the air phase is blue color and yellow color. It is a water phase. The second method to simulate microplastics behavior on your nature. Uh, this study using ANSYS learned by combined VOF model and DPS model, and VOF model simulates multi-phase fluids by showing a single cycle momentum equation and monitoring the volume fraction of the ice fluid. And a decrease model to simulation particle motion we can define by equation 1. In equation 1 we can explain some parameter FD is transport and U is velocity and UP is the velocity of particle and rho p and rho this is it is density of particle and density of fluid, and fs is inner force. In figure 1 we can define FD by equation 2. In equation 2 we have V is a fluid dynamics of viscosity, and IE, and this is a Reynolds number we can define by equation 3. And beside a city we can this is a brass coefficient we can define by equation 4. And boundary condition initial VOF model using Stokeways for the theory with height weight equal 0.15 meter and wavelength equal 1.5 meter, and beside degree phase model using property particle have three sides. It include 0.2 millimeter and 1 millimeter and 5 millimeter with different density. We have 900, 1000 and 1100 kilogram per meter cube. Result and discussion. The first, Olorians profile velocity and streamline. In figure 4, this shows your vertical velocity profile for non-structure. We have the blue line, and with structure we have 2K, WS2, WS2 and WS1, and for black line and red line, difference between WS1 and WS2 it is high structure. WS1 high equal 0.2 meter and WS2 high equal 0.28 meter. The vertical velocity profile at location of the submerged structure, we have WS1 and WS2 is similar with the strong shear layer developed about it equal 0.2 meter, and for non-structure NS shear layer with an increased magnitude about it equals 0.3 meter in the near shore. And figure 5 is so the streamlines for KNS and WS1 and WS2. In the figure 8, we can see when non-structure, we got only 3 streamline. Sorry, we have 3 recycle. However, and we have one recycle is very small. But when we using structure, beside increase high structure, we can see so increase recycle. When increase high structure, we can see recycle is larger than another case, and also increase recycle. And divergence and curve of figure 6 and figure 7 show divergence and curve for 3K, NS and WS1 and WS2. We will consider for 3K structure and non-structure. When in figure 6, when we have structure and increase structure, increase high structure, we can see divergence. It is reduced. Is reduced. And however, in curve, when we increase high structure, we can see magnitude of curve or velocity is increase. This meaning is opposite with divergence. Lagrangian trajectory of particle. This slide shows trajectory of particle really at x and y equals 7.5 and 0.28 meter for 3K, NS and WS1 and WS2, with density is constant equal 900 kilogram per meter cube, and with different size, we can see blue color is equal 0.2 millimeter, and black color equal 1 millimeter, and red color equals 5 millimeter. And this case shows the density is equal 1000 kilogram per meter cube, and this case is also so 3K. This slide also 3K. Also show 3K for non-structure, NS1 and WS1 and WS2. This case we can see is fast structure onto behavior of microplastics. When have structure of microplastics almost motion active in on the slope. And this slide shows animation particle have density equal 1000 kilogram per meter cube, and is similar color. We have a blue is equal 0.2 millimeter, and black color equal 1 millimeter, and 5 millimeter is red color. And mean trajectory of particle in figure 11 shows the mean trajectory particularly on the near surface and near shore. For high density and large size, is meaning 5 millimeter particle or the mean horizontal displace upstream was greater in the case of non-structure. We can see figures 4a and 4b and 4c, and also greater displacement upstream and downstream were observed in the WS1 and WS2. We can see figure 4D and figure 4G. The high density particle and move to the bottom as the size increase, but small size equal 0.2 millimeter, and high density particle it tend to move to near shore for KWS2 and WS1, while NS it tend to absorb. It depend size and density. For density is the same water. It equal 1000. We can see figure B and figure E and figure S on density. In this case, activities around deep water equal 0.1 to 0.3 meter, and move to the offshore. And the low density equal 900. We can see particles tend to move offshore. It's meaning backward, but distribution almost in the deep water from 0.2 to 0.3 meter, and activity in the intermediate water zone. Final conclusion. First, small size particle with a size of equal 0.2 millimeter show a high dispersion rate and will even distribute regardless of your density. And the second, heavy particle with a density of equal 1100, and large particle with a size of equal 5 millimeter show a weak horizontal dispersion rate and did not transport throughout the structure because they did not respond after sinking to the bottom. Yes, thank you so much. See you next conference. Thank you.